Thanks, Ricky. So my name is Denise Blankenberger. I'm a graduate research fellow at the Energy Studies and Buildings Laboratory at the University of Oregon. And I'm in the second year of my Master of Architecture degree and the first year of my Master of Science in Architecture degree. And I'm in finals week right now, so bear with me. And this is a project that I'm working on that was supported by the Agricultural Research Station through OSU and University of Oregon, which we call the Tallwood Design Institute. And the PI on this project is my advisor, Kevin van de Moemelenberg, who's also the director of the ESBL at U of O and an associate professor of architecture. And the topic of this discussion will be net zero energy and its implication on mass timber buildings. So I'm going to start with a brief overview of the importance of the comfort and energy performance, especially from a net zero energy perspective, and this will be really expanding on what Colin had already touched on. So net zero energy is mostly driven by some ordinances in California that are dictating that all new commercial buildings by 2020 have to be net zero. So that's why this is really important, and this is where the market is going. And then I'll move forward to illustrate some sort of case studies that we're using environmental energy simulation performance to see how night ventilation of mass, or NVM, can be applied to this. And near the end, I'll touch on an ongoing human factors subject that's also funded through this grant about human thermal comfort and the overlay of visual comfort to see how psychology sort of plays a role in all of these things. And then we'll end with future research and where all of this is going. So one of the exciting opportunities of using mass timber in buildings is the carbon sequestration properties, and I'm sure most of you are familiar with this, but so when a tree is growing and while it's alive, it's actually taking in the carbon from its environment, and then you sustainably harvest and process the tree, use it in your buildings, and in theory, assuming the building doesn't burn down or biodegrade, that carbon stays locked up for the whole lifespan of the building. By contrast, we have concrete, which is a high embodied energy material that produces a lot of carbon, mostly through the production of the cement mixture, which the cement industry itself actually accounts for 7 to 8% of the world's total CO2 emissions. So any chance that we can to cut down our use of concrete is highly encouraged. However, over the lifespan of any building, the operational energy has actually both the largest impact on the environment and the highest economic cost. And the embodied energy is what goes into powering the building and its ongoing energy needed just to function over the course of 10, 20, 30, 100 years into the future. And that far outweighs the initial embodied energy and carbon emissions that you save by using timber over, say, concrete. And so while we reap the benefits of the carbon sequestration early on in the process, we need to make sure that the building is actually efficient enough so that that sustainability story sort of continues throughout the lifespan of the building and not just from ground up. So what we see when we break this down, another lovely pie chart for you, and Colin sort of did touch on this. For your standard sort of to code best practices building, about 56, maybe even up to 60% of the building is driven by heating and cooling, which takes a big portion of the annual energy consumption. And when you add in all the fans and pumps also necessary to make this happen, it continues to grow. And all of these loads, the 56% that's highlighted there, is impacted by human thermal comfort, which human thermal comfort is a pretty tricky thing to understand, and it's impacted by these 6 major factors, which is clothing, airspeed, air temperature, radiant temperature, metabolic rate, and humidity. And we know it's a lot more, more finicky than that. Your ethnic background, your gender, your height, weight, everything sort of plays into that, and sometimes just your thermal preference. Some people prefer to be hotter or colder at certain times. So it can be kind of tricky, and that's why it takes so much control at the building level to manage human thermal comfort. And then the 4 things that the building can impact are humidity, airspeed, air temperature, and radiant temperature. So by comparison, when you look at a net zero energy building, what used to be 40 and 70%, or 40 and 7% respectively for heating and cooling is now dropped down to 3 and 2%. So those are just the loads specifically for thermal comfort, and all of that is just by reducing the operational energy of the building. And now all those other things that were just microscopic on the other pie chart are now what's really driving the energy use in the net zero building. So this is representative of the Bullitt building in Seattle. So, and then again, this is with California making net zero mandatory, this is why it's really important to cut down any operation loads that we can and shrink down that portion of the pie chart. So if you think of that first pie chart, on the far left, you can see the Bullitt building is just a little tiny blip, and the gray mass over top of it is how large of a PV array would be necessary to power the building's annual loads exclusively with a photovoltaic array. And then Seattle building codes are a little bit more stringent. So if you build the Bullitt Center to those sort of building codes, it shrinks that down a little bit, but it's still outrageous and still impossible to do localized at the building level. And even, we're all familiar with LEED, Leadership in Environmental Design. That still is too much to be done really at the local building level, and you would have to bring in outside energy in order to power it. But what was actually designed by Miller-Hull is what's still a pretty large overhang and still had to meet some sort of zoning requirements and some sort of loosened restrictions there in order to get that built, but that's what powers the building annually. So in order to get to that point, you have to reduce the loads significantly just in order to power the reduced pie chart that I showed previously. And then a big portion of this is thermal mass, and that's where I'm going next. So the New Buildings Institute actually highlighted a few key strategies that all or nearly all net zero energy buildings use in order to achieve these drastically reduced loads. Daylighting was number 1, and number 2 is aggressive natural ventilation, including night flush ventilation of thermal mass for cooling. And there's 2 components to this, which are in the title itself, ventilation and thermal mass. So the way this works, during the nighttime hours, you open all the windows and you have cool air being forced in and through the building, and then the mass that's stored up, or the heat that's stored in the thermal mass of the building is released slowly over the nighttime hours, which heats it when the heat is necessary during the evening. And then during the daytime, you seal it up super tight, and then that thermal mass gains heat from lights, people, and the sun itself, and stores it over time until you open up back again at night, and then it's slowly released with that airflow through the building. And night flush ventilation has also been shown to have a sort of stabilizing effect, which leads to more human thermal comfort, which again helps to reduce those energy loads from the get-go. And the key thing to successful night ventilation is thermal mass, and a lot of it exposed. So typically this takes the form of about 4-inch concrete in walls, floors, and ceilings, and has to be about 2 to 2.5 times the square footage of the floor area. And there's a few examples of mass timber buildings that actually use night flush ventilation. And we've discussed Bullitt on the left-hand side, designed by Miller-Hull, which uses nail-laminated timber and concrete for thermal mass and abundant airflow to make this work. Rocky Mountain Institute, designed by ZGF, uses cross-laminated timber on the second floor deck and concrete, again, for thermal mass. But what's important to note is that these are more sort of demonstrative buildings. They're very expensive, but they're more to show what is possible. And the next goal is to make the art of the possible, the art of the more so realized, and especially if we're trying to market this towards the California climate and making all new commercial buildings net zero, this is going to have to be way more approachable than some of the sort of more expensive strategies that these buildings have used to achieve the net zero status. And in some cases, these are just far too complex, far too expensive to be implemented in your sort of everyday building. For instance, the Bullitt Center uses exterior automated blinds, and Rocky Mountain Institute uses phase change material in the light shelves and the walls. And the hyper chair, which is a chair with heating and cooling embedded in the chair itself, so you can really control your personal comfort, or electrochromic glass or motorized blinds. These are all things that aren't super approachable and not really feasible to do in every building. So that's what we set out to figure out, how to find a sort of balance between these two things. And by doing so, we looked at a couple case studies. And this building is here in Portland, Albina Yard, which is a really great office building designed by our friends at Lever Architecture. So we took this and ran a few energy simulations to see how it would perform if it were designed with night flush ventilation in mind. So we're looking at the 4th floor, again, where friends at Lever Architecture actually work. And it's actually designed to what you're seeing on the right-hand side, a CLT concrete hybrid. So it's got the CLT floor with a concrete topper. But then we also tested it if it were just a CLT assembly without the concrete, just for comparison. And so this is your pretty standard engineering chart and this is what designers would use, dictated by ASHRAE, to determine the sort of peak energy loads in the building. So on the left-hand vertical column, you have the temperature, on the outdoor air temperature, and on the x-axis, you have the time. And so here we're just plotting the CLT construction, and you can see that it's it's fairly hot. It starts at 85 degrees or so, climbs to about 88 on the average day, and even more so on an extreme day. And when we add the concrete topper, it's actually pretty encouraging. It drops by about 5 degrees on your average day just for a 2-inch concrete slab, which is pretty significant. However, we have our tool, the predicted mean vote, or PMV, which tells us what we would expect people to judge the thermal environment. So the red dots are too warm, the green is comfortable, and blue is too cool. And we obviously don't have any too cool days. And for the most part, it is still fairly warm in this assembly. And this is assuming that the building was designed without any mechanical cooling, and it's relying entirely on these passive elements, which is not realistic. Again, the building does have cooling. We're not like nuking our friends over at Lever. But there's still room for improvement. So we tested a couple other strategies to see if we could sort of mitigate this temperature and bring it down. And one of those was with increased ventilation by adding more window area, which, long story short, wasn't really successful. And that's mostly due in part to the fact that the cross-section of the floor is just much too deep to get any sort of cross-ventilation. If it were somewhat narrower, or if there was stacked ventilation or something that allows the airflow to happen a lot more drastically, then it might be more feasible. But in this instance, it just wasn't designed for that purpose. So some other sort of remediation technique might be necessary. So the takeaway here is that design matters, and wood doesn't have the same thermal mass of that of concrete. And in this case, the building is just going to have to rely on mechanical cooling. So let's look at another building and walk through the same sort of series of analyses. And this building was actually designed with night flush ventilation in mind, and it was designed with concrete. This is the Health and Wellness Building at Lane County Community College, designed by SRG. And you can see the sort of ventilation pathways that go over and across the ceiling to cool the concrete slab. There's this architectural element, the stack ventilation, that actually, again, draws air up and through the assembly. And we'll backtrack a couple steps. So instead of starting with CLT, we're going to start with your sort of code metal frame building. And this actually also has concrete floors. So without night flush ventilation at all, you can see this is really, the heat comes into the building, gets locked in there, and it has nowhere to go, so it stays really hot during all occupied hours in the building. And then when you add night flush ventilation, the indoor air temperature begins to mimic that of the outdoor. And surprisingly enough, it's actually fairly comfortable in here based on this graph. And what you'll see is that during the design day, it's for the most part fairly comfortable, although I wouldn't really say that climbing between 80 and 90 degrees would be extremely comfortable in my opinion. But so let's move forward to timber and see how it compares. And so what we see is about the same discrepancy between the two assemblies with the Albina yard model, about 5 degrees drop on average on just a design day, and even more so on the extreme day, which makes it much more feasible. And then if you run the same simulation with concrete as the building was designed, you see that drops down even more so, and the temperature decreases about 7 degrees on average on the design day from that of the timber building assembly. So thermal mass matters. So the takeaway here is that, again, we know that wood is not going to perform as well as concrete for thermal mass. And we're not looking to disprove science. Like, we know that the specific heat of concrete is next to 0 and the density is really, really high, whereas timber has a fairly high specific heat but a really low density. So that's where the trade-off happens. So that's where the concrete CLT hybrid comes in handy and then sort of mitigates that. So the other takeaway is that we are looking at or sort of expanding on those hybrid strategies and possibly looking at other ways of approaching like more strategies that you can sort of retrofit in the building. Some more drastic things like earth tubes or stacked ventilation might be things that are the most effective at controlling peak cooling loads, but those would have to be early on decisions in the design process, and you can't really retrofit earth tubes in a building. You can retrofit fans, maybe phase change material, and automated blinds, but those would be very small changes and not really driving the demands of the building. But we're going to continue to investigate other things that might be the best practices, approaches. But then the next thing that we're beginning to question is the notion that psychology can impact thermal comfort. And there's preliminary evidence that supports that wood can promote increased thermal comfort due to the human tendency to perceive a sort of warmth with wood materials. And this works the other way as well, that you might feel sort of cooler in the warmer months when you're exposed to a wood environment. And this is our standard chart for thermal comfort. So if I were to sort of take a poll of the room right now and ask you on a scale of 1 to 7, and this was P.V. Fanger's scale that was created in the 70s, I believe. He literally wrote the book on thermal comfort, so this is our standard across the board. So in any given time, not everyone is going to be 100% comfortable. So this is the sort of range that we'll look at, with -3 being too cold and +3 being too warm, and the steps in between with 0 being thermally neutral in the middle. So the theory, if we apply this to wood being a warm material, is that at the same temperature, if you give someone a white or like a typical wall assembly and ask them how cold or warm they are, and they say -1, if you give them that same temperature but a different sort of visual environment, they might perceive themselves to feel warmer in that sort of environment. So it's basically a sort of forgiveness factor that could sort of give a little bit more wiggle room to what would be our expected thermal comfort curve. And to address this question, we're doing an original human factors study using 2 different physical wall treatments, white gypsum and Doug Fir CLT panels, to determine the perceived thermal comfort in 2 very different thermal environments. So we have a cohort of about 20 to 30 or so participants. They go in 2 at a time in our climate chamber here in Portland, which I'll explain in a second. And each participant sees both a wood treatment and a white wall treatment, and they experience both heating and cooling on 2 separate days. And each experiment is about 4 hours long, which is broken into 2 halves. And we modify the environment in the climate chamber to bring both extremes, not plus and minus 3, but plus and minus 2. So it does get to what most people would say would be too warm or too cold. And we start at neutral and slowly increase or slowly decrease the temperature, bringing them back to thermally neutral at the half. So we do this with radiant panels. The climate chamber is a retrofitted walk-in refrigerator that we have radiant panels that modify the climate, or we can change the airspeed, relative humidity, air temperature, but this all happens with radiant heating, so it's sort of subtle and happens over time, and you're not forcing hot air or cold air on people, which is how these thermal comfort experiments are typically run, so this is a little bit unique. So we have participants go in pairs, and they take surveys every 20 minutes to gauge their thermal comfort. And we're also collecting blood pressure and continuous heart rate monitoring, so we can later determine if there's a sort of stress-reducing factor of the wood wall assemblies as well. And in this way, sort of by analyzing the transient environment, it's not so steady state, and it's more indicative of what people might actually experience in a sort of normal interior environment. Let me see. Okay. Yeah, we have a really ingenious lab tech that came up with a way of, oh my. Anyways, we have 2-sided panels. So the 8x12 room is outfitted in these panels, so we can just flip them, vice versa. One side has the gypsum assembly, and one side has the Doug fir. So that looks really awful. There it is. So the participants never see this happening, so when they return for their second day of testing, they're immersed in a completely different environment. And all this can happen in 20 to 30 minutes or so. So it's pretty exciting. And so far, the results are pretty encouraging. The gray curve, or those gray dots, that's the environment that we're forcing on the participants and what would be the sort of predicted level of comfort based on the plus and minus 3 chart on the left. The blue dots are the gypsum wall votes, and the orange dots are the wood wall votes. And you can see our sort of trend lines there. The orange is typically below that of wood is lower than that of the gypsum. And this might look like kind of a lot of data. This is only about half of our cohort so far, and we haven't even dug into the rest of the questionnaires. This is just one question for, at this moment, how are you feeling? So there's a lot of more data that we have to dig into, and a lot more research that can happen in this sort of field. So it's exciting, it's new, and we're learning an awful lot. So the next steps for this project specifically are to finish up our winter cohort of participants, and then we're going to rerun it again in the summer to see if there's a sort of seasonal discrepancy between the winter and the summer. And then we're going to continue to build on those energy simulations to see if we can maybe get net zero a little bit more applicable and bring it down to market rate. So thank you.